let us start a next topic named as Discrete Time Fourier Transforms. From this session, for next few sessions, we will look at what is DTFT, what is its significance, how to calculate the discrete time Fourier transform of various signals given, what is its significance, how does it differ from a normal continuous time Fourier transform, all those things we will see in the coming sessions. So, let us start with small introduction to what is DTFT, and then let us understand a discrete time Fourier transforms. Okay, let us start with the introduction. As you all are aware, there are two types of signals. One is a continuous time signal and second one is a discrete time signal. So, for both continuous time and discrete time signals, what are the different transforms which are useful? That is what we are going to see in this introduction. There are two types of signals. One is continuous time signals, as we have seen. The second type is discrete time signal. A signal may be analyzed with the help of Fourier series and Fourier transforms. Basically, Fourier series is used for periodic signals and Fourier transform is used for aperiodic signals. Fourier transform, note, may be used for both periodic and aperiodic signals. That means, if I see, there are two types of signals. Okay. One is continuous and the second one is discrete. Okay, these are the two types of signals. I can have a continuous time signal and I can have a discrete time signal. As you all are aware, in continuous time we will use this symbol and for this we use the symbol N. Okay, these are, and when I use a Fourier series, I use for a Fourier series, generally this is for a periodic signals. Okay, whenever a signal is non-periodic or aperiodic, then I use Fourier transform. I use a Fourier transform here, and Fourier transform generally I can use for both non-periodic and also for periodic signals. That is the significance of Fourier transform, as you have all studied earlier. So, Fourier series basically only for periodic signals. Generally, whenever a signal is non-periodic or aperiodic, I will use a Fourier transform for this. But Fourier transform can also used for periodic and also non-periodic signals. This is about Fourier series and Fourier transforms. Now, let us see the next one. Fourier series is a continuous time signals. It is called as a continuous time Fourier series. Fourier transform for a continuous time signals is called as a continuous time Fourier transform. And Fourier transform for a discontinuous time signals is called as a discontinuous time Fourier transform or discrete time Fourier transforms. Okay, discontinuous means discrete. So, if I apply a Fourier series, okay, let us use the short form. Fourier series means Fs. If I use this for a continuous time signal, then it will become a CTFS. That means it is continuous time Fourier series. Similarly, if I use a Fourier transform, I call it as Ft, and this is for continuous, then this will become CTFT. In short, that is continuous time Fourier transform. Now, so let us say I am using a Fourier transform for a discrete time, okay, or a discontinuous time, then this will become DTFT. So, this is our topic for this session and the following sessions. That means, when I find the Fourier transform for discrete time signal, then that results in a discrete time Fourier transform, and that is what we are going to discuss in this session. Now, let us see discrete time Fourier transforms in detail. Okay, let us take a discrete signal x of n. Then what will be discrete time Fourier transform? How does it look like? Okay, that is what is going to be our discussion now. So, let there be a discrete time periodic signal x of n, then x of e to the power of j omega is given by summation n is equal to minus infinity plus infinity x of n e to the power of minus j omega n. Here the function x of e to the power of j omega acts as a spectral function which shows the relative amounts of various exponential components of x of n. Okay. So, let us write this. So, x of e to the power of j omega is given by a summation n is equal to minus infinity plus infinity x of n e to the power of minus j omega n. That is, this summation gives us exponential components of x of n. That relation is given by this x of e j omega. So, as you know this is a spectrum. So, this will give you a spectrum of a discontinuous aperiodic signal x of n, that is equal to summation n is equal to minus infinity plus infinity x of n e to the power of minus j omega m. This is the representation of a DTFT, that is DTFT, that is discrete time Fourier transform of x of n is given by x of e to the power of j omega and is given by this formula. So, this is how we get the discrete time Fourier transform of a signal x of n which is aperiodic. Now, x of e to the power of j omega is called the discrete time Fourier transform of x of n. X of n is called the inverse discrete time Fourier transform, that is IDTFT of x of e to the power of j omega. DTFT of x of e to the power of j omega is periodic with a period 2 pi. So, any interval of length 2 pi is sufficient for the complete specification of the spectrum. Note, generally the spectrum is drawn in the fundamental interval of minus pi to plus pi. The range of integration is always 2 pi. So, this is called as DTFT as we have seen, and if I want to calculate x of n given this, that means given this I want to calculate this. So, that becomes what is called as a inverse DTFT, okay, and the integration limits is always limited to a range of 2 pi. In general, what we do is we represent the spectrum in a period of minus pi to plus pi, okay. So, I can represent any signal, the spectrum is periodic with a period of 2 pi. That is one of the significant features of DTFT. So, this is about it. I will just read that explanation which I have done. DTFT x of e to the power j omega is periodic with a period 2 pi. So, any interval of length 2 pi is sufficient for the complete specification of the spectrum. So, you have a big spectrum that extends from minus infinity to plus infinity, it is okay, but it is getting repeated with a period of 2 pi. So, once I can draw a spectrum on the limit 0 to 2 pi, then it is a repetition of that. So, the whole representation can be done in interval of minus pi to pi, the integration is minus pi to pi, or it is limited to period of 2 pi. Let us see features or points of discrete time Fourier transform. The first point is the discrete time Fourier transform x of e to the power of j omega of a discrete time signal x of n is expressed as we have just written on the board, x of e to the power of j omega is equal to summation n is equal to minus infinity to plus infinity x of n e to the power of minus j omega n, or DTFT of x of n is nothing but x of e to the power of j omega. So, this is one point which you should remember. That means x of e to the power of j omega is given by summation minus into plus infinity x of n e to the power of minus j omega n, that is one. Or I can write discrete time Fourier transform as we have done earlier, discrete time Fourier x of n is nothing but x of e to the power of j omega. So, this is a representation of a discrete time Fourier transform. Once we do this, we know what is x of e to the power of j omega, we can calculate from this formula given x of n. So, this is how we calculate the discrete time Fourier transform of a given sequence of x of n. That is one of the features. The other feature is the inverse discrete time Fourier transform called as IDTFT is expressed as x of n is equal to 1 by 2 pi integral minus pi to plus pi x of e to the power of j omega e to the power of j omega n d omega. So, given x of e to the power of j omega, how do I calculate x of n? That is called as inverse discrete time Fourier transform and is given by 1 by 2 pi, that is a period in which existing. The interval is minus pi to plus pi x of e to the power of j omega e to the power of j omega n d of omega. So, this will give me the inverse DTFT, that is inverse discrete time Fourier transform. The inverse discrete time Fourier transform is given by this, that is x of n, that is nothing but inverse Fourier. So, I can write this like this. So, I can write this as inverse discrete time Fourier transform of x of e to the power of j omega, that is nothing but x of n. So, this is given by 1 by 2 pi, that is the whole spectrum is represented with a periodicity of 1 by 2 pi, that is what we are putting. The period is the period is 2 pi and its existing integration limits are minus pi to plus pi x of e to the power of j omega, that is what is given, and it is multiplied by e to the power of j omega n and d omega. So, this will give me the inverse discrete time Fourier transform, whereas this give me the discrete Fourier transform. This is discrete time Fourier transform of x of n, and this is inverse discrete time Fourier transform of x of e to the power of j omega. So, you get these two. Once you these two formulae, you can calculate given x of n, you can find out what is the discrete time Fourier transform, or given discrete time Fourier transform, I can find out x of n by calculating the inverse discrete time Fourier transform. So, these are the two formulae which we should remember. So, from these two equations we can say that x of n and x of e to the power of j omega form a discrete time Fourier transform pair. So, I can write this as like this. So, x of n will have x of e to the power of j omega, okay, and x of e to the power of j omega will have a x of n. That means, from x of n I will calculate this is discrete time Fourier transform, and from this I calculate x of n, that will become inverse discrete time Fourier transform. So, these two form a discrete time Fourier transform pair. The discrete time Fourier transform x of e to the power of j omega is the frequency domain representation of x of n, and the inverse discrete Fourier transform x of n given by 1 by 2 pi integral minus pi to plus pi x of e to the power of j omega, e to the power of j omega and d omega is called the synthesis equation. The synthesis equation indicates that an aperiodic signal x of n may be represented as a linear combination of complex exponential infinitesimally close in frequency. So, I will just see this. When I look at this, this will give me the frequency spectrum of x of n. This whole equation is called as a synthesis equation, okay, synthesis equation, where the complex exponential terms are relatively very close to each other. So, this is called a synthesis equation, and this actually represents the frequency spectrum. X of e to the power j omega actually is a representation, frequency domain representation of x of n. That is, given x of n, when you want it to convert into a frequency domain representation, x of e to the power j omega does it. And actually x of n is also called a synthesis equation, because it is indication that it is a summation of closely related which are nearby to each other, closely related frequency components, that is summation. Like CTFT, the frequency spectrum discrete time Fourier transform is also continuous in nature. Okay, CTFT Fourier transform is continuous, DTFT is also continuous. So, what is the difference between a CTFT and DTFT? I will read the differences here. The difference is the frequency spectrum is not periodic in continuous time Fourier spectrums, whereas in DTFT the frequency spectrum x of e to the power j omega is periodic with a period 2 pi, and the synthesis equation x of n involves an integration only over a frequency interval that produces distinct complex exponential only 2 pi. So, the difference is, now when you look at a continuous time Fourier transform and a discrete time Fourier transform, then this is periodic, that is a major difference. Okay, it is periodic with a period 2 pi. Okay, and if you look at the synthesis equation x of n, what are we doing? In synthesis equation, if you remember, the integral is from minus pi to plus pi and 1 by 2 pi. This indicates that it is a periodic signal, isn't it? So, this is very important difference between the DTFT and the CTFT. Now, when do we say a discrete time Fourier transform exists? Okay, let us see the conditions under which the discrete time Fourier transform exists, or which are needed for a discrete time Fourier transform to exist. Okay, let us see this. The discrete time Fourier transform is given by x of e to the power of j omega is equal to summation of n is equal to minus to plus infinity x of n e to the power of minus j omega n. Now, e to the power of minus j omega n mod is equal to 1. According to the above equation, the existence of DTFT is guaranteed if x of n is absolutely summable. Okay, so that means DTFT exists only when this converges. Okay, that means the mod of e to the power of minus j omega n is 1. So, for this DTFT to exist, x of n must be absolutely summable. Mathematically, what is happening here? Summation n is equal to minus 1 to plus infinity, mod of x of n must be less than infinity. That means it should converge rather than diverge. Okay, it may be noted that this condition is sufficient, but is not the necessary condition for the existence of x of e to the power of j omega. So, that means when I sum this, n is equal to minus infinity plus infinity, mod of x of n must be less than infinity. That means this is absolutely summable. The value must be less than infinity. When this happens, then there exists a DTFT. Okay. So, this is the condition for which a DTFT must exist. Okay. This is one of the conditions. So, we generally say this to be satisfied to get a DTFT. Okay. Otherwise, also in some cases it can exist, but this is not a necessary condition, but one desirable condition. So, once you get that desirable condition, then DTFT does exist for this type of summation.